This problem has been labeled as an LC circuit, and we have the Vmax here. Note that this is not the generator, so this is literally an ideal LC that will be oscillating sort of at full potentials there. And we've got a couple of questions here. The first thing is asking for the period. So we should know that the period equations, there's two of them. We got 2 pi over W, or 2 pi square root of LC. The problem is we don't know the inductance. That's something we may want to solve for at some point. Now we are given Vmax and the capacitance. So with that in mind, we should be able to remember that the Vcmax is equal to Imax times this XC thing. And we actually know Imax as well, so we can sort of move this over here. And we should be able to get what XC equals. So Vmax is 250 negative 3. Divide that by 7.5. So we get 100 over 3 for this XC value. We know XC is actually 1 over WC, so we might be able to figure out what this W is from all this. So if we have 100 divided by 3 equals 1 over WC, we'll put the W on this side, and we'll basically just say that W equals 3 divided by 100C. All right, so we can go ahead and try to calculate that right there. 3 divided by 100 times the capacitance. So we get this crazy number here, but that's what W is. You might want to mark that down as well. 136,363.64. This is reds per second. And now we can use that. So we go 2 pi divided by the answer. So we'll have a period of 4.61 e to the negative 5 seconds. All right. Now for the next thing, this UE max, this is the maximum energy across the capacitor. We could consider 1/2 and then Q squared over C, or we could consider CV squared over 2. And because we have the V and the C, that's going to be the one we probably want to use. So we'll say UE max is going to be equal to 220 nanofarads times the voltage squared is 250. And then we'll divide that by 2. So that should give us the UE max. Negative 9 times 250 to the negative 3rd squared. Divide that by 2. So we'll get 6.875 nanojoules here. And for the UB max, well, UB max is going to be more like 1/2 L I squared. And this would probably be a max, right? So that would be the UB max. And we still don't really know what L is, but we do know that an LC circuit has a oscillating frequency as the resonance. So we're able to sort of say that that W is actually equal to 1 over square root of LC. So we can actually sort of rearrange this. W squared equals 1 over LC. And then we could be able to solve for the inductance equals 1 over W squared C. So let's use that equation to figure out what the inductance is. 1 over W squared is 363.64 squared times the C, which is 220 negative 9. So we get our inductance is 2.44 e to the negative 4 henries. And so we can use that in here if you want. So you can go ahead, divide that by 2, multiply that by the Imax, which is going to be 7.5 negative 3 squared. And we should get the same answer that we did over here, 6.875 nanojoules. Perfect. Now for di over dt max, Well, we had this equation for the voltage of a capacitor, but there's another equation for the voltage of the inductor. The L max is going to be equal to L times the di over dt max. It's another equation we should have written somewhere. But we can rearrange this equation, dividing L on this side, and we should be able to get the di over dt by using the voltage max, which is this one, 250, -3, divide that by the inductance now that we have that. And that's just going to equal 1024.6 for the amps per second. We'll be going through here. And then we also have the du dB max. All right, well, this one might be a little bit more interesting. The key to this last one is to realize that the UB is equal to 1/2 L, and then the time varying function of this I, this current. And this is for any time. Now what we can do is take the time derivative of that. Okay, so we'll take derivative on this side as well. Here we have to plug in the I of t before we can take the derivative or anything. And we should know I of t is equal to I max times the sine of Wt plus the phase constant, which we'll just call 0 for now. Now if we're going to square that, then we'll have this, and now we can sort of plug that in. So we'll say that we're going to want to take the time derivative of 1/2 L, and then there's a I max squared sine squared Wt. Now this stuff is constant, so we'll pull it out of the derivative, and we'll just focus on this. And if we were to try, hey, actually, this is a constant as well, so we'll just focus only on this part right here. So to derive sine squared, we kind of want to pull this squared out of the parentheses. We'll put it over here. So that way we can kind of see that this whole thing is, you can put the 2 over here, and then you put the sine Wt in there. And then you're going to take the chain rule. So inside of here, what's the derivative of sine? It is cosine of Wt. And then we also have to take the chain rule again of what's in there, so that's going to be the W. Awesome, so that's going to be the derivative of sine squared. Then we have the I max squared still, we have the L, and we have a 1/2. And that is going to be the time derivative of the UB. All of this stuff. There is one small little thing that we can simplify real quick. In here, we see 2 sine cosine. That can actually simplify to sine of 2 Wt. That's cool and all. And then we'll still have a W. We'll still have the I max squared and an L and a 1/2. And now, well, if we want the maximum of the time varying function, then we just get rid of this stuff. We make that equal to 1, and we'll get the maximum. So now this is technically what the maximum energy is, or the change in the energy, really. So that would be 1/2 times the inductance, which is 2.44 to -4, and then times the I max squared, which is going to be 7.5 milliamps squared. And then there's still a W in the end here. Times the W. What is the W again? It is 136,363.64. Okay, and so we get that the changing energy here is going to be 9.36 e to the -4. And this is joules per second, and joules per seconds can also be called watts. So that'd be